troubleshooting protocol problems. Now, in order for two network hosts to communicate, they have to be using the same network protocol. Therefore, if you have an IP-based network with IP-based routers and servers and other IP-based hosts, and you go ahead and install a workstation on that network and you configure it with a different protocol, then it's not going to be able to communicate with any other host. Everything has to be using the same network protocol. In addition, if you do decide to use an IP protocol on your network, then your IP network configuration settings have to be made correctly. For example, all of the hosts on the same logical network have to be using the same network address. The network portion of the IP address on every single host must be the same in order for them to communicate. Now, on this network, we have 4 different hosts, a server and 3 workstations. The server is assigned an IP address of 192.168.1.1, and these 3 hosts are assigned 192.168.1.2 and 192.168.1.3. And this other host over here is assigned an IP address of 192.168.2.4. Now, to determine which hosts are going to be able to communicate with each other, you need to determine the correct subnet address. Now, if the network uses classful addressing, we can look at the first octet and determine what the default subnet mask is. Now, in this case, the server's IP address starts with 192. And because this network uses classful addressing, we know that this is a Class C address. The first 3 octets are the network portion of the address, while the last octet is the host portion of the address. Now, these 3 hosts all have the same network address, 192.168.1.0. Therefore, they'll be able to communicate with each other. Now, this host over here, however, will not, because it uses a 2 in the 3rd octet. Therefore, this host is using a completely different network address of 192.168.2.0. Therefore, it's not going to be able to communicate with the other hosts on this network. Now, let's take a look at another example. Now, here our server is assigned an address of 10.0.0.1, and this host is assigned an address of 10.0.0.2. This other host is assigned an address of 10.0.0.3, and this host over here is assigned an address of 10.200.1.4. Now, in order to determine which of these hosts will be able to communicate and which won't, we need to look at the IP address and determine what class it is. Now, again, we're going to assume that this network uses classful addressing. Well, this address starts with a 10, and if it uses classful addressing, then this is a Class A address. Therefore, only the first octet is actually used for the network portion of the address. These 3 octets are the host portion of the IP address. So in this case, the addresses are actually configured such that all these hosts will be able to communicate. This is very important because if you don't pay attention to the address class, your first inclination may be to assume that this host has an invalid address because the 2nd and 3rd octets are different. But in this case, that's not correct. In order to ensure that they're on the same network, you need to make sure that every host in the network uses the same subnet mask, regardless of whether you're using classless or classful IP addressing. Now, if your IP addresses are configured correctly, then the network portion of each IP address on each host will be the same if you use the correct mask. But if you use the wrong mask, then the hosts are not going to be able to communicate, even though the addresses may appear to be configured correctly. Remember, the subnet mask defines which portion of the address is network and which portion is node. Now, in the previous 2 examples we looked at, we assumed that all the hosts were configured with the default classful subnet mask, and that those masks were configured correctly. However, if you use an incorrect prefix, or if you don't calculate your subnet boundaries correctly, then again, communications aren't going to work. In this example, suppose we're going to use a 22-bit prefix on this network, which is equivalent to using a subnet mask of 255.255.252.0. In this configuration, these 3 hosts will be able to communicate with each other. By using a mask of 255.255.252.0, we can actually define up to 64 total subnets within this address space. Remember, 172.17 is a Class B address by default. However, what we've done is steal an additional 6 bits from the host portion of the address to create these additional subnets. Therefore, you've got to know where the subnet boundaries reside. Now, because all of these addresses look like valid Class B addresses on the surface, it's it's actually quite easy to miss the fact that one of these hosts is actually on a different subnet than the others. Now, in this example, our subnet boundaries are 172.17.0.0, 172.17.4.0, 172.17.8.0, and so on. In order to determine your subnet boundaries, you can use an online subnet calculator. When you do, we'll see that this host here will not be able to communicate with the other hosts on the network because it's on a completely different logical network. Its subnet address is 172.17.4.0 instead of 172.17.0.0. Now, if your host needs to communicate with other IP hosts outside of your local network segment, then there's another parameter that you have to configure correctly, and that is the default gateway router address. Now, understand that when you send information from one IP host to another IP host on the network, the IP protocol on your system will first check to see if the destination computer resides on the same local subnet or whether it resides on a completely different subnet. Now, it does this by looking at the source and destination IP addresses along with the subnet masks. If the destination host resides on the same network as the sending host, then the IP protocol will use ARP to determine the appropriate MAC address and directly deliver the data. However, if it determines that the destination host resides on a completely different IP network, then the IP protocol will immediately forward that data to the default gateway router address, and then let the router deliver the information to the appropriate destination host. Now, this can be a problem if the wrong gateway router address has been configured. If this happens, then you're going to notice a couple of common symptoms. First of all, the host will be able to communicate correctly with the other hosts on the local network segment, but the host will not be able to communicate with hosts on another network segment, including the internet. A key mistake that's commonly made and something that you need to remember is that the address that's assigned to the default gateway router has to reside on the same logical subnet as the host that's using it. You need to check the default gateway address and verify that it's configured with an IP address and subnet mask that's appropriate for your local subnet. And you need to make sure that it is the correct IP address. Another common problem revolves around DNS name resolution. You need to make sure that the correct DNS server address has been configured for name resolution. For example, if you find that you can ping a remote host by its IP address, but you can't ping that host by its DNS host name, then something's wrong with your name resolution system. It could be caused by several different things. One thing you should check first is whether or not the host has been configured with the correct DNS server IP address. In addition to DNS issues, you also need to be concerned with DHCP issues on an IP network. DHCP problems can cause serious protocol issues if the DHCP server is misconfigured. The DHCP server, remember, hands out IP addresses, subnet masks, the default gateway address, as well as DNS server addresses to the host on your network. When the host comes up on the network, it gets this IP addressing information from the DHCP server. Now, problems can occur if that host cannot contact the DHCP server when it comes online. Modern operating systems, including Windows, Linux, and Mac OS, can let a protocol called a PIPA take over if an address can't be configured from a DHCP server. Now, let's suppose we have a DHCP service running in this network, and it's built into our network switch. We've configured our workstations here to use DHCP to get their IP addressing information. Now, in most networks, our servers, our routers, and our other network infrastructure devices are usually assigned a static IP address. They don't use DHCP. In this situation, we can potentially have a problem if the DHCP server stops working. Suppose the firmware inside our switch here experiences a fault and the DHCP server goes down for some reason. When this happens, hosts can no longer get an IP address when they're powered on. So at this point, a PIPA takes over and the DHCP clients will get an address starting with 169.254. Now, when this happens, all of the hosts on our network that received an PIPA address can still communicate with each other, but they cannot communicate with our infrastructure devices. For example, they can't communicate with our file server, nor can they communicate with our default gateway router because they're assigned a static IP address. And because our workstations are using a PIPA assigned addresses and our infrastructure devices are using statically assigned addresses, they're now running on two different logical subnets. Really, with the PIPA, the goal is to automatically assign IP addresses to network hosts such that if something happens to the DHCP server, they still get an IP address. Now, theoretically, this should allow them to continue to operate and communicate. However, in this scenario, these three hosts will be able to communicate using their APIPA assigned IP addresses, but they'll not be able to communicate with any of our critical infrastructure devices that use statically assigned IP addresses. Now, the problem here is that being able to communicate between workstations really isn't all that useful. Users on these workstations need to be able to access their files, they need to be able to send print jobs to printers, they need to access their email, and they need to access other services that are hosted on our servers. In addition, access to the internet requires the ability to communicate with this network's default gateway router. Therefore, when APIPA takes over, these workstations lose communications with all of these infrastructure devices. And therefore, what they can do is not a whole lot. Now, another DHCP problem that happens occasionally is that of a rogue DHCP server. Now, this can occur in several different situations. One of the most common examples is one where somebody installs a server operating system. Perhaps they're doing some testing, they've installed a server operating system in, say, a virtual machine. Now, without realizing it, they may accidentally enable the DHCP service on that server. I've even seen situations where a rogue DHCP server can be accidentally enabled by an end user who's configured their mobile phone to function as a hotspot. Now, this can disrupt network communications because some of our network hosts are going to get their IP address from the rogue DHCP server, while our other hosts get an address from the legitimate DHCP server. Now, because the rogue DHCP server wasn't configured properly, it's very likely that it's handing out incorrect IP addresses. When this happens, some workstations can communicate with the server or the router, and others can't because they're getting the wrong IP addressing information. That's it for this lesson. In this lesson, we talked about troubleshooting the IP configuration. We looked at using the correct IP addresses. We looked at using the correct subnet mask. We talked about the importance of configuring the correct default gateway router address. We talked about configuring the correct DNS server address. And then we ended this lesson by talking about how to resolve common DHCP problems.